remind you, I pointed out that once you have the Z of J, that can be expanded in a Taylor series. So when like n is equal to 0 to infinity, 5 to the power n upon n factorial. Then we had the nth order term will have something like integral dx1 all the way up to dxn. Then we'll have n factors of j, which I call, let us say, j1 to jn, times the Green's function, which I will denote as the average of this phi 1 to phi. And this is what we are really after, and that was represented as this phi 1 to phi n is taken to be the path integral average. I mean, I'll just put proportional because it is this normalization factor which is not relevant. D phi 1 to phi n e to the I times the free action plus I in lambda by 4 factorial integral dx by 4. Okay, this is what we did yesterday. Then I said that depending on what quantity you want to compute, you pick the corresponding term from here. For example, if you want to talk about a particle going from one place to another, you create the particle and then destroy the particle. So you would like to have J1 and J2. Then what you need to look at is phi 1, phi 2 average. And phi 1, phi 2 average will have a phi 1 and phi 2 here. We can't compute that path integral, so you do it in perturbation series. So there are two series expansions involved here. First, you decide what kind of process you are looking at. It could be just a propagation, it could be 3 pi mesons scattering off to 3 pi mesons, or it could be 2 of them scattering off to 2. Then depending on which process you are thinking of, you know how many J's you want. Okay? Then you know which term you are looking at. And that will tell you that many phi should be there. So then you need to evaluate this particular object. That particular process is described by this amplitude. But because you cannot compute this process exactly, you do one more thing, you do it in order by order. Okay? So we did one example yesterday, that of just the Green function, that is a 2-point function. So today let me start with the 4-point function, because that will bring us to this renormalization and things like that. So I want to now look at a process where in this result there are 4 terms. So I am looking at a term which involves dx1, dx2, dx3, dx4, j1, j2, j3, j4, and phi 1, phi 2, phi 3, phi 4. So this is what yesterday I symbolically represented by a block like this with 4 legs, which are at x1, x2, x3, x4. Okay. So this represents 2 particles scattering off into 2 other final states, and this is what we are looking at. And this involves all the interactions of the scattering to infinite orders in the coupling case. So that would have phi 1, phi 2, phi 3, phi 4 here, and which we want to evaluate. So we will do it both at linear order and at quadratic order, just to gain some experience. So let us first look at it in linear order. So if you are doing it in linear order, what we want to compute is, here you are retaining only up to linear order. So you will just have I lambda, this is 4 factorial. You will have I lambda upon 4 factorial. Then you will need to compute, of course there is an integral over d4x finally. You want to compute the average which is given by phi 1, phi 2, phi 3, phi 4, then I have a phi 4 evaluated at x. Let me just go through this once again. So this is what we want to do. Now you already know that because it is, so once you have brought it down, this average is computed with free here. So this average, to be precise, is computed with lambda not equal to 0, while these averages are computed with lambda equals 0 because this is in perturbation. This lambda goes away and it's just free this. And the free action is quadratic, therefore I just have to take the pairs. So let us again play that same game. As I said, this is just like programming or some kind of a handicraft, so you just have to gain some experience with it. So let us just try to do that. So you want to, there are 8 of them and you want to pair them. And what kind of pairings can happen? First, I can pair phi 1 with phi 2. So that would correspond to something like x1, x2. Actually at this stage we have reduced it to a previously solved problem. Once I have done that, then it is a phi 3, phi 4, phi 4x. This is what happened in the 2-point function. Because if you are doing 2-point function, there will be only 2 phi's. So we had already done it, but let us go through it once again. So phi 1 and phi 2 I have paired. Then phi 3, phi 4, either you can have the kind of diagrams in which the x3 is paired with x4. Then this has to take care of itself. And that will be a pairing where x is paired to x and x is paired to x. Okay, this is the figure you will get. Yesterday we got 18, now we will have 180. Okay, so there is one more line coming from the phi 1. Then similarly, you can have a situation where phi 1 and phi 2 are paired, which is this line. But here we don't pair these two, but we pair it with one of the x's. So then that is phi 3, x3 to x, then x2, x4, then an x2, x loop. Right? Because this also yesterday we had. We are not interested in this, we are not interested in this, because these are disconnected diagrams. Just some vacuum bubble. This is actually going to be important, but I am not going to discuss this. That will give you mass renormalization. Okay, well, probably if I have time, I will do it tomorrow. What is really interesting is the pairing in which we don't pair the, see any other pairing, like instead of pairing phi 1 with phi 2, phi 1 with phi 3, etc., all of them are going to give you the same. So what we are interested in is pairing phi 1 with one of the phi of x. Okay? Then what can you do with the rest? You can still pair these two. The moment you have done that, that will again give you a line. So we are not interested in it. So I don't want to draw all those diagrams. Only non-trivial diagram you will have is each one of them has to pair with one of the x's. Okay. So that is a nice diagram because that is going to give you x1 to x, x2 to x, x3 to x, and x4 to x. I mean, it doesn't matter how I label that. So this, yeah, this is a very interesting, physically meaningful diagram. Namely, it tells you that x1, a particle propagated from x1 to x, another particle was propagating from x3 to x. They interacted there. Then from there it went to x2 and another particle went to x1. This is a most elementary, intuitive way of thinking about a scatter. So what is the amplitude for this? This is what we want to compute. So what would be the amplitude? We can immediately write it down. The term which we are interested in will be I lambda upon 4 factorial integral d4x. Phi 1 is paired with phi x, so that is x1 x, similarly x2 x, x3 x, x4 x. and where they meet to interact is left to you, and you can integrate over d4x. Now you can easily convince yourself that this can be done in 4 factorial ways, because I could have paired this with any of the 4. Once you are done it, the next one can go in 3 ways, the other one can go in 2 ways, and the last one is unique. So the total contribution, if you are looking at this 4 factorial, will go away. Okay, that is why we put it in the first place. So you have this. So this can be computed. You just write down the expression for it and integrate. Once again, it is nice to look at this in the momentum space. So suppose I call this quantity as g of x1, x2, x3, x4, and suppose I do its Fourier transform in all the 4 variables. Okay. Here a little bit of conventions would help, but okay, I will do one convention here and then switch. Maybe I should do it now itself. It is convenient to write this as x2, x3 and x2, x4. Let me explain why. See, when you go to momentum, you would like to put arrows saying that there is some inflowing momentum and outflowing. Now, normally people would have put an arrow here, and put an outgoing arrow here. But that is a little tricky, because the way the propagator was written, if you are saying that particle went from x1 to x and then x2 to x, the arrows should be in the same direction. But that is not what we mean physically, but it is symmetric. Therefore, it doesn't matter how you write, but it is much nicer to write it in this way. Then when you do the Fourier transform and you use the convention that it is always e to the ip left minus right in the x minus x1, use some sensible convention. The P1 and P2 and the P3 and P4 will come with opposite sign. So the Dirac delta function looks more meaningful. Otherwise, you have to flip this sign. So it is just that convention. So we will do it like this. And then I want to do the Fourier transform of this on x1, x2, x3, x4. Okay? What will I get? So let us look at the left hand side itself. The left hand side has I lambda d4x. Now I am going to write each one of them in Fourier space. So I am going to have an integral over dp1 upon 2 by 4, dp2 upon 2 by 4, dp3 and dp4, 2 by 4. So all the 4 quantities are going to be written in Fourier space. So I have a g of p1, which I will call g1, times our convention, let us say, is e to the I p1 x1 minus x. I just have to use it consistently, that is all. Then I have a g2 e to the I p2 x2 minus x. Then I will have a g3 e to the I p3. Now it is x minus x3, and g4 e to the I p4 x minus x3. Okay. Now what do I have? When I am thinking of it in Fourier space, I am going to do a Fourier transform on x1, x2, x3, x4 with an integral over all these things. So that just goes away, right? So that quantity, all these 4 which I laboriously wrote down, just go away, and the x1 goes away, x2 goes away, x3 goes away, x4 goes away. Okay? But remember that when I am taking away this, there are these minus sign hanging around. That should go into this. That should go into this. Then all that I am left with is a d4x integration over p1, p2, p3, p4 with minus signs flared. Therefore, you will end up getting just a Dirac delta function times all the g's. So what I will have is 2 pi to the power 4 Dirac delta function P1 plus P2 minus P3 minus P4 times G of P1, that was what I called G1, G of P2, G of P3, G of P4. So this is very nice because this is what that amplitude is in the momentum space. And so that is why momentum space Feynman rules are very easy. This is one case where there is no loop. So there is no internal integration. Remember yesterday we did a 2-point function. One of those diagrams had this diagram, had an integration over that P because that momentum was not fixed. Here all that we are saying is that this corresponds to a diagram like this, where you have a momentum P1, momentum P2 flowing in, and momentum P3 and momentum P4. Okay, and this vertex corresponds to should be a minus sign somewhere. I mean just for okay. So just to be proper, this is how it is defined. So that will be a minus. Not that it matters, but by convention, this quantity is given a minus I lambda at the vertex. So in the Feynman rules, I told you that the convention is not to put these G's of the external legs because they just go for a ride. So we won't write it down. And one overall momentum conservation also you don't write down. So the amplitude for this is extremely trivial. The amplitude for this process in the momentum space is minus I lambda. Okay. But this is physically quite important. Suppose you take the mesons and you scatter them, then you can, in principle, calculate that scattering amplitude. I mean, of course, there will be cross sections, this, that, what the detector does, etc. But ultimately, you can calculate this amplitude. That tells you what a coupling constant is. So the operational meaning of the parameter which we have introduced into the Lagrangian is by taking this physical process and calculating its amplitude. In other words, if I take this particular process, the amplitudes for that is what defines for me what the coupling constant is. Okay. So this is important when we get divergent contribution to lambda because we have to physically regularize it. I will show you how to do that. Okay. So this is the first part. Now let us do the same thing to quadratic next order, that is to the square of lambda. Okay. So quadratic order, this is remaining the same because we are still computing the 4-point function, but we want to take this quantity to the next order in lambda square. So what we will have is one more 5. So we'll have to deal with 12 5s together. Okay, but I'm not going to do anything beyond that. So we'll stop at that. So we'll let us do it up to order lambda. Okay. So what is involved here? What is involved here is that first I will get on the outside. So let us try to do it a bit slowly. Minus I lambda upon 4 factorial this square. Then I will have an integral over d4x. Then I will also have an integral over d4y. Then I am going to have phi 1, phi 2, phi 3, phi 4, phi at x to the power 4, phi at y to the power 4. Okay. Now let us fix the, just like that 4 factorial went, here also the 4 factorial square will go. So the way to see this is the following. Let us look at the different kinds of pairings you can have. It's actually fairly obvious. There are 2 of them here. So what you do is that you take this phi 1 and you connect it with any of these. Okay, first of all, whatever I do with x, I can now do with y as well. So there is a factor 2 arising out of it, which I will put first. Then with phi 1, I can connect this with 4 different ways. Then the phi 2 can go to 3 of them, right? And we would like to have this phi 3 go into this in the same 4 different ways, and this going into this one in 3 different ways. So I already get 4 into 3 and another 4 into 3. what is left? So 2 of this has gone into 2 of this, 2 of this has gone into 2 of this. Then I want these to be connected. I don't want anything which is contracted in itself, because that will be a disconnected diagram. That can be done in 2 different ways. There are 2 left here and 2 left here. One can be connected with either one of them, the other one is unique. So I get another factor. So this is just 4 factorial square. Okay. So I can just stick with one diagram and forget all this. So this 4 factorial square goes away. Oh, I forgot to put a half. That is because when I do it to quadratic order, it is e to the x, which is x square by 2 factorial. Okay, so there is a factor. This is what you have. Now let us see what further things we can do. So diagrammatically, what have we done? We have taken a phi 1, which is at x1, and I have connected it to x. This is x. Then I have a phi 2, which is connected to x. Then phi 3 was connected to y. I mean, that is x3 to some y. And then x4 is connected to y. Then x and y are connected twice. This is the diagram we have. So the way to think about this is that every vertex you must have 4 lines, because that is what lambda phi 4 tells you. That phi 4 tells you there are 4 lines meeting at every vertex. So you draw this and they have 4 vertex, and here also there are 4. And you think of the only way you can connect them up without any disconnected pieces coming in. Okay, and this is the only way to do that. So this is what we want to study. Now what is the amplitude for this is what we want to look at. Okay? Fine. Now of course again, now that you are all veterans in Feynman diagrams, I can just write down the expression in momentum space, but we can also try to see what it will give, just for fun. So this is going to be minus I lambda the whole square 1 by 2 d4x d4y. Let us see what is the amplitude for this. This will be x1 x x3. Okay, how would I like to write that? Okay, so x2 x2, that is fine. And similarly x3y. You can just look at this diagram and write it down. y2 x4. Okay, but then it is multiplied by an xy and an xy. Could have written it as yx if you want to, but it doesn't. Okay, this is what we have. Now, what will this look in momentum space? Let us try to figure that out. So we have to do exactly the same kind of game again. This quantity is again g of x1, x2, x3, x4. There are only 4 of them, and we have to do the Fourier transform on all of them. Okay? You can probably guess, but let me try to write it down since it's just 1 or 2 of them which we are doing. So what it will have, if I take the Fourier transform, is minus I lambda the whole square. Then I have a half. Then I have an integral over dx and an integral over dy, this is d4x, d4y. Then each one of them I have to write as propagators. So I have 4 propagators, so it is integral dp1, this underline is supposed to mean 2 pi to the power 4, dp2, and they are all going to go away in a minute. So dp3, dp4, all of them will go away when I do the Fourier transform. So I am just writing it down for fun. Then you are left with there are xy integral. They are not going to go away. So there I will introduce a dp and a dq. Okay? Then we want to write down each one of them. So this is g1 e to the I p1 into, let us say, left minus right, which is x1 minus x. Then I have a g2, is it g2? Yeah, g2 into the I p2. I took it as x minus x2, but if it turns out that the standard convention is different, we will flip it in the end. Then I have g3 e to the I p3 x3 minus y, and a g4 e to the I p4 y minus x4. Then I have two more, which I have called g of p, gp e to the I p x minus y. Then let me write the next one, which is gq e to the iq x minus. This is what we want to compute. Okay? So let us see what all we have. We have an integration over x and integration over y. So let us do that first. So if I do the integration over x, I get a p1 here and I get a p2 with the opposite sign. Okay? So I actually should have written it as x2 minus x1 because I don't want p1 and p2 to come in as sign. So let me make it as x2 minus x using that symmetry. So that is fine. Then I have, there is no x here, there is an x here and there is an x here. Okay, this is what we have. So that will give me a Dirac-Delta function minus I lambda a whole square. Actually the final expression is going to be quite simple, but I am just trying to get to that. So there is a p, all the x terms let us take out. So that will be a Dirac-Delta function on P1. I have to keep all these integrals outside. So there are all the, so there is a dy integration and all the p integrations. Okay, I'll just put a square bracket around it to say that there is all these p integrations. Okay. Then I'm just going to do the x integration first. So that will give me 2 pi to the power 4 delta function of, there is going to be a p1 plus p2 I am doing x, so this is plus p plus q, right? So essentially the x1s have disappeared, the p1s have sort of, one of them can be used to integrate this out, but we will do that in a minute. Similarly now let us do the y integration. So if I do the y integration, again I am going to get, so here I have done the x integration, so I should about these x's. Okay. Now I am going to do the y integration. So when I do the y integration, I get a P3 and a P4 and P and Q all with the same sign. So I get the Dirac-Delta function of P3 plus P4 plus P plus Q. And 2 pi to the power 4. Right? So that takes care of y, this y factor, Then I have another y factor here and another y factor here. Okay? What did I do wrong?
That should be x4.
Oh, sorry.
P.
Minus x4. That's good. Okay? Now, I don't care about this x1, x2, x3, x4. Okay? Now, this x4 came with the wrong sign because I forgot to write
P3
it
will have
flip down.
actually.
Okay, so assume that this is plus x4. Okay? So that just gives me, once I do the Fourier transform on the left hand side, they are all going to go away. So I don't care about that. So I can rub these guys off completely, saying I have done the Fourier transform, which means these go away, as I told you. Okay? Of course, I have to retain all the g's. So I have a g1, g2, g3, g4. They will also disappear because then the external legs are going to be cut off. So that is fine. So this is what you are left with. And in this, now I am left with only a dp dq integration. dp, dq, and then all these factors. So this product is now here. Okay? Now, what does this mean? Okay, first of all, we know that P1 plus P2 has to be equal to minus of this, and P3 plus P4 should also be equal to minus of that. That means the derived data functions can be replaced by saying P1 plus P2 should be equal to minus P3, P4. So one of them can just come out. Okay? So that just goes away. 2.4 derived data function of P1 plus P2 minus P3 minus P4. That is the overall thing. So these are the things which I am going to finally ignore, so it doesn't matter. So what is left is just this GP and GQ. Okay? Now since these are the same, it is nicer to write in terms of ingoing momenta, which is P1 and P2. Now what does this tell you? This is something absolutely trivial. What it tells you is that you can do one integral immediately. So you get all the things which is waiting outside, minus I lambda, the whole square, half. Then I have a G1, G2, G3, G4, and overall derived data function 2 pi to the power 4 derived data function of, I'll just call it P1 plus P2 minus P3 minus P4. You are left with this integral, in which let me do just one integral and leave the other one. So I will have a dp over 2 pi to the power 4. Q integration I can do using this derived data function. So I have a g of p and g of q is replaced by P1 plus P2 minus P. Okay? That either P3, P4, or when I change I should put a minus sign. So this is what you will have. Q is negative of that, so that is going to be this. This one is physically very, very simple to understand, even though we did this in such a horribly complicated way. So what is the theory about Feynman rules? You don't put this overall derived data function, you don't put the external legs, then you will have 1 minus I lambda for each of the vertices, and this factor just comes from permutation in the order. So you will have a minus I lambda to the power square. This is the only non-trivial thing. What is this? What that is, we can immediately draw from this picture. Suppose I have a P1 going here, P2 going here. It is exactly this diagram in momentum space. P3 here and a P4 here. Okay. Now at every vertex I have to conserve momentum. So at this vertex I have okay, P1 plus P2, and suppose I introduce for this the momentum P. Okay, I should put let just be okay. Let me keep P2 here. So it is the momentum P is going in here. There is a momentum P2 coming here, momentum P1 coming here. P is taken care of by this. The remaining quantity is P1 plus P2 minus P, which is on this. Okay, and that sum is also equal to P3 P4. So what it is telling you is that you have a loop which you want to evaluate. You assign a given momentum to this, assign to the other one the sum of these two momentum minus that remaining momentum. You can do this in various permutations. Because the total momentum is conserved, you could have replaced this by something else. And you could have used a sign convention where the arrows are opposite direction, then it will become minus, etc., etc. But the reason I sort of try to force it into this form is that people before us has defined a set of variables for such scattering processes, which are P1 plus P2 the whole square. P is called P1 minus P3 the whole square, and there is a variable called U called P1 minus P4 the whole square. These are called Mandelstam variables, which is important in classical scattering theory. As far as we are concerned, they are just labels. Okay, so if you have a scattering where two particles with momenta P1 and P2 coming, four momenta P1 and P2 coming, and they go out with momenta P3 and P4, it is conventional to define these variables and work with them. This has some nice properties. For example, you can compute S plus T plus U, and you will find that it is 4 times M1 square plus M2 square plus M3 square plus M4 square, etc. So you can represent them like an equilateral triangle. S, T, U are the perpendicular distances from any point inside. Okay, and things like that can be done, and they can be related to center of mass energy and scattering angles and various things. We won't need any of this because we are not going to do scattering theory. But these are the three scalars which you can build out of. For our purpose, what is important is just this factor. This factor and of course this factor, which defines for us the amplitude to the next order. To the lowest order, we wrote down the amplitude somewhere. It is just minus I lambda. Now to the next order, this is the amplitude which we get. Okay, we have to still evaluate that integral. That is where all the fun lies, and that will diverge. So here, if you take the diagram in this form, you get this. And there is a reason people introduce these variables. They introduce these variables because if the theory has some symmetries like time reversal and things like that, then if you compute the amplitude for that, there are other processes which are obtained by interchanging particles which will have the same kind of amplitude. Okay, except for some converse conjugations and things like that. So in particular, this is just one of the diagrams which we have drawn. You could have another diagram in which you keep one particle fixed, and instead of this P2 you can replace it by any of these two. So you can replace P2 by P4 or P2 by P3. When you do that, P2 is replaced by P3. It will come with a minus sign because P2 was ingoing and P3 was outgoing. S will become T. If you replace this by P4, S will become U. So if I compute this quantity with P1 plus P2, which corresponds to S, because after all, once you do the integral, the result can depend only on because of Lorentz invariance, only invariant quantity left there. P1 plus P2 is a 4 vector. So the result can only be a function of P1 plus P2 the whole square. So this entire object has to be some function of S. Right? Similarly, if I had done it for a process in which P2 is replaced by P4, I would have got exactly the same function with S replaced by T. Another one will be S replaced by U. Because these are the same diagrams with the labels reversed. So the total amplitude will be minus I lambda square half F at S plus F at T plus F at T. That is what the total amplitude. That is what we want to compute. Which means I want to evaluate this. Okay. Now we are going. there is a very rigorous way of evaluating this. When you evaluate, it will diverge, and there is a way of regularizing that divergence. And we have done our usual cutoff, which is what I will do today. But one last bit which I want to teach, which I will probably do tomorrow, is a process called dimensional regularization. Now, in the dimensional regularization, this integral can be evaluated in a, okay, why am I saying it is divergent? That is obvious, because g of p is some 1 over p square minus m square. So this is going to be similarly, there will be this quantity square. So when you are looking at large values of p, you will have a 1 over p square and an 1 over p square. It will have an 1 over p4 integrated over d4p. So that is going to be a logarithmically divergent term. Okay, so it is divergent. Now what we will do is to isolate the divergent part and the convergent part very nicely in the dimensional regularization method, and then work with the finite part, and you will get the same result which I am going to get today. Today I am going to take a slightly cruder approach. I will just use a hand waving argument to get you the kind of structure which will emerge, and that will be justified rigorously by the other process. But this I want to do because I want you to get a physical feel as to how this lambda renormalization works. And yesterday Sanved was asking whether we will get the same result which we found by the other method. So I wanted to show that you get the same, some 3 over 32 pi square, etc. by this procedure. Okay, that is what we are going to do. Okay, so let us start with this. What is the nature of that integral, and how can we sort of do a cutoff regularization of it? So I have this object which is integral over d4p. So let me write down the whole thing. I have minus I lambda the whole square half integral over d4p divided by 2 pi to the power 4. And let us look at, first let us write down what exactly it is. It is I divided by p square minus m square plus I epsilon. Then you have I divided by some capital, okay, let me call this some capital P, which is, okay, let me use capital P minus small p. Capital P just stands for the sum of p1 plus p2 the whole square minus m square plus I epsilon. This is the integral which I want to evaluate. Okay. So what I am going to say is that I am only interested in the divergent structure right now, and I will scale it with p square in order for dimensional purposes, because p square is the quantity which is s, which is what I expect the answer to depend on. So that we will do in the last minute. But let us look at the divergent structure of this term. To get the divergent structure, you only have to take the large p limit. So I can ignore this capital P from this P. That will come in the end for scaling. Therefore, this quantity is same as this quantity, and I will give me a minus sign. That minus sign will take away the I square minus sign. So this is what you have. Now I do the Euclidean rotation. Then this becomes this quantity. This becomes plus P square. And I am interested in the large p square limit. So all these goes away, and it is p to the power 4. Yes. So this is extra for an extra I factor. You get an I because you are going from the real to Euclidean. That picks up an I. The original I's do not survive. All of them go away. But this I comes from the integral. So what is this integral? We just want to get the constants right. That is why we are doing it like this. I lambda square, then there is a factor 2 here, then I have a 1 over 16 pi to the power 4, then I have the volume element of a 4-dimensional sphere times p cube dp. Volume element of a 4-dimensional sphere happens to be 2 pi square. Then I have a integral of p cube dp divided by p4, so that is log p at the cutoff. Okay. Therefore, I would like to write this as log p square and put another factor 2. and I use an upper cutoff, which will be some lambda, which has dimensions of square of the mass, divided by the lower cutoff I would take to be the scaling variable. Yes, this is p square. It is this part which is a little bit of cheating, not cheating, it is knowing the answer and writing it down, because it is logarithm and you want to scale it with some factor s, which is some finite quantity, and that is going to be that p square. So the argument is that when you separate it out into divergent part and the finite part will have an s dependence, and that will precisely come with this s here. Okay, that is not clear at this stage, but that is what will happen. But it has to have dimensions, and I could have put any other quantity and that finite thing can be taken out. So let us see what this gives. So this is 2 goes to 32, and this pi square goes, and there is a pi square. This is what you have. Okay, some lambda divided by this s. Okay, so this s I have defined as p square, so there is no problem. Now what does this mean? Okay, let us get to the physics. So this is the amplitude which we have got. So what we are now saying is that the amplitude for this scattering to order lambda square is given by minus I lambda, then I get plus I lambda square upon 32 pi square times log of lambda by s. This is what you get when we do this. But then I told you that if you interchange, you will get a t and then you will get a u. Okay? So there are plus log lambda by t plus log lambda by u. Let me go through that argument once again. What we computed here is the process with P1 plus P2 sitting here. Correct? That came in for this particular scattering process. Then I said there are 2 more processes closely related to that which we have to count in, because we want to take into account all the 2 by 2 scattering processes. So the other process are obtained by retaining any one P1, and then instead of P2 replacing it by P4 or P3. That will lead to P2 being replaced by either minus P3, because outgoing is being replaced by ingoing, or P2 being replaced by this. So the only difference here will be instead of P1 plus P2, I would have got P1 minus P3, or I would have got P1 minus P4. So I will get the same answer with S replaced by T or U. So this is what we have, and as advertised it is infinite, because we are supposed to take lambda going to infinity. Okay. Now we will do the same thing which we did before. What we will say is that, look, you have to define your coupling constant by a scattering process. Now when you do this scattering process, what the scattering process recognizes is something with a blob here. To the lowest order it would give you minus I lambda, next order it might give you something else, etc. But all of them are thrown. So you have to fix what is your coupling constant by doing the scattering experiment at some value. Let us take that value to be S0, T0, U0. Okay? And you define your coupling constant. So what we will do is to say that the observed or physical coupling constant, let us say minus I lambda physical, is defined through this amplitude. So that is equal to minus I lambda plus I lambda square by 32 pi square. Let me call that entire quantity as some function which depends on lambda, and it also depends on S, T, U. So we are defining this physical quantity by evaluating this at some value S0, T0, U0. Okay. Then we solve for the parameter lambda from this. So what will I get? So this gives me, if I, okay, actually I need minus I lambda. So minus I lambda is given by, so you bring it to this side, minus I lambda physical minus I lambda square upon 32 pi square f of the cutoff S0 T0 unit. All that I have done is to take it to this side. So it is minus I lambda physical minus this quantity is minus I lambda. Now this is all to order lambda cubed, or actually lambda cubed there is no contribution, but it doesn't matter. It is of order lambda cubed. Okay. So to the same order lambda cubed, you can replace this by lambda physical. It's just the iterative way of solving for this. Okay. So you have got this. Now let us write down what that amplitude is. So now we are calculating the scattering amplitudes at some arbitrary S, T and U. You do some scattering experiment and you get this result. This is the answer. But we don't want the answer in terms of some Greek letter in the Lagrangian, but we want it in terms of something which somebody has observed. Somebody has found that the lambda physical at, they know the value of this, it is 0.3, when S0, T0, T0 has some particular value. So we are going to rewrite it in terms of that. So we substitute for this. So when you substitute for that, minus I lambda becomes minus I lambda physical minus I lambda physical square upon 32 pi square f of lambda S0 U0. Then you have that extra term which is plus I lambda square, which to the lowest order again is lambda physical square upon 32 pi square. That quantity is f of lambda S T U. Okay, that's what you have. Now, here is the miracle of the logarithms. If you take this quantity and you calculate it explicitly, you get minus I lambda physical square upon 32 pi square times this minus this is what we want to calculate. So you take this expression with S0, T0, U0 and subtract from it with S, T and U, and the lambdas just go. So I just try to get the right sign there. So what do I get? If I put minus here, then it is this quantity minus the one with that, right? So this quantity is going to have 1 upon S0 kind of terms, and I am subtracting from it the terms with S, so this will become log S by S0 plus log T by T0 So this is your answer. What it tells you is the following. Suppose you do the scattering experiment where the P1, P2, P3, P4, which is what you will say. You want to know, I want to know what is the scattering amplitude for two particles to go in with momenta P1, P2 and come out with momenta P3 and P4. Instead of that, since the overall momentum is conserved and the answers are going to depend only on Lorentz invariant quantities, you could have said that I am thinking of a scattering experiment characterized by the variables S, T and U having certain values, 2 GeV, 4 GeV, 18 GeV kind of a thing. And you want to know what that amplitude is. Now what you need to know is, you need to know what is the coupling constant of the interaction measured at some energy. So some guy will do that experiment and will tell you that if S0, T0, U0 are your values, then the lambda physical is 3 or 0.3. Then you want to know it for any other value, you plug it and you get the answer. So your divergence has completely disappeared. Okay? And you will find that this is exactly the factor which you had even in the previous analysis. So one way of saying this is, suppose you go back to this result or any of these. Okay, doesn't matter. Now if you think of this quantities S0, T0, U0 being scaled by a factor mu, okay, then all the logarithms will pick up that factor mu. So even more precisely, suppose you scale it with a factor mu1 and you scale it by a factor mu2. Then you will pick up a log mu2 by mu1, and that is how the lambda will change. And if you work it out, you will find that it tells you that the lambda minus what would it be? 3 lambda square upon 32 pi square log mu. Should be a constant. The factor 3 comes because you will get a log mu in each one of them, and everything else is there. And if you go back to your notes, you will find this is what we have found previously. Okay. So if you can write it more precisely as lambda at mu1 minus this quantity at mu1 is equal to lambda at mu2 times this, so that mu1 by mu2 is what is going to give you lambda 1 minus lambda 2. Okay. So from this you can calculate how lambda runs with log mu, etc., etc. So this is exactly what your perturbative renormalization would be. So in the conventional theories, what they would have said is that, okay, let us go and compute this process. To the lowest order it is this. Then you want to add to it a process like this, P1, P2, P3, P4, and this one at the same point. Okay, and there is an internal momentum here which need to be integrated out, and as a result of which you will get the amplitude for this plus amplitude for this. Amplitude for this is minus y lambda. The amplitude for this, as I said, you could have just written it down. By the way, we have verified the consistency of the Feynman rules. See, the Feynman rule said you put minus I lambda for each vertex, throw away the external legs. Every internal momentum has to be determined by the conservation law. If there is any one momentum which cannot be determined, you have to integrate over all of them. Okay? So if I apply it to this, I get a result which is what we have evaluated, that integral. At the same time, if I had originally written down that entire expression and laboriously calculated the Fourier transform, I get the same thing. So that tells you that when you keep drawing newer and newer diagrams, you don't have to keep inventing the Feynman rules. It just takes care of itself. This is all which is required, because everything has been reduced down to contracting pairs of the phi's. The moment you contract pair of the phi's, you will get x1, x2 kind of object, and the Fourier transform of that will have the e to the ip factors, and any integral which just flows through that will give you factors like g1, g2, g3, g4. They don't care because you are going to drop them in the end. And the only things which you cannot take out are the internal loop integrals, where the p is not fixed, and they get integrated. Okay? So you would have drawn this diagram, and you would have drawn the another diagram, etc., etc. And when you compute it, you would have found that this diverges. So the moment you find it is divergence and there is some logarithmic divergence, you reabsorb that into your redefinition of lambda. I just try to do this more physically by taking this. This is the way, for example, Z in his quantum field theory in a nutshell describes it. It's a nice description of this. He uses exactly the same kind of an idea and tells you that when you do this in terms of the physical quantity, the divergences just disappear. This is what happens. Now, there are a couple of minor comments. See, this is a diagram which has two vertices. Okay? But you can have a diagram like this. Take this diagram which has just one vertex here and you put a loop here. Okay? So there is one more vertex here. Now, to be very, very precise, I should consider all diagrams of order lambda square which involves 4 external particles and then compute the thing. I haven't done that. That is because I'm sort of cutting short on some of the things which, if you are interested, you can read in textbooks. What is going to happen here is that suppose I just break it here. Okay? What does it mean? It means that there is this diagram which we have computed, and then there is another 2-point diagram with a correction. Okay? So if you use, what would this correction do? If I have time, I will show it to you tomorrow. The kind of corrections like this, or even 2 loops, 3 loops, etc., they can all be summed up as a geometric progression, and that just changes the mass parameter to a renormalized value. So if you use, when you are doing all these computations, the way we have done this computation, mass has disappeared because we looked at only the divergent piece. There is a finite piece. See, this is not the really important thing, because this is important only to show that you can renormalize. After you have renormalized, you want to know what the answer is, and that answer is given by the finite part. This is just like when we did QED, or rather the QED using the scalar fields and electromagnetic field interaction by the effective action method. We found that you have an effective Lagrangian. That effective Lagrangian has one divergence which we threw away by subtracting -1. Then there was another divergence which was proportional to E square minus B square, which we used to redefine the E and thereby redefine the charge. Then we went off into a tangent and we talked about how charge renormalization works and how charge runs, etc., etc. But the really interesting experimental quantity would be after these two divergences have been removed, granted that it can be done, there is a finite part, and that finite part is when you Taylor expand, gives you that 7 by 4 E square minus B square the whole square plus some E dot B the whole square, etc. So this is the quantity which you are really after, and you vary that, it will tell you the corrections to electromagnetic field, etc. Similarly, there is a non-trivial finite part which, if you actually calculate it correctly, will involve the mass. Okay? Then the question arises, what mass do you put there? Because mass was also a parameter in your problem. So mass will also get renormalized, and if you use the physically observed mass in the finite part and the physically observed lambda effective, then everything will be taken care of. And the process of renormalizing the mass takes care of a host of diagrams like this. Okay? So that is why I haven't drawn that. This is one good thing about this intuitive way of working with Feynman diagrams. It sort of tells you at a glance what are the relevant pieces and what are the irrelevant pieces. And in this particular case, this is clearly the relevant piece which you should have, and then you should compute things. So we will just have one class tomorrow, which probably tomorrow I will take only half an hour or something. I mean, I can't finish it now, but I need a little bit more time, and then that we will wind up. Any questions? Come on.
So when we what will we do with the capital P minus P square term?
Capital P. Oh, what I did was to say that when you do that integral, there is going to be some, suppose you integrate it from some point up to, let us say, some capital P or whatever. Then you do the integral from capital P to infinity, and assume that capital P is large, or there is, you introduce an intermediate scaling point. I have only concentrated on the divergent part of the integral. So the divergent part is just log lambda plus a finite quantity. That finite quantity I have not even computed, and that log lambda, because of dimensional reason, should be log lambda divided by some momentum square, and I have just used P square as the scaling variable. This part, as I said, I will justify it tomorrow more rigorously, in the sense that there is a way of regularizing that integral without making any of these approximations. Then you will pick up a term which is divergent, and another term, and the dimensional regularization method will introduce a scale with a dimension mu in it, and then one can actually show that all these results follow from it.
Then nu is equal to lambda by s is equal to lambda by t is equal to lambda by.
Which one?
The nu that you introduced.
Yeah. No, it is not lambda by s. What I am saying is that you have that amplitude. Let us evaluate that amplitude at some scale s, and then you evaluate it at another scale mu times s. That is mu times s, mu times t, mu times that is scale all the momenta by mu. Okay, then the s t u will scale by mu square. I mean, I don't remember whether I used mu or mu square. Maybe it is mu square, so it will be actually 16 pi square. Yeah, that is probably the correct expression. Okay, so whether you want to scale with mu, scale the momenta or square of the momenta, but once you rescale them, all the three of them will get rescaled by that factor, and that will tell you how the physical coupling constant changes with the scale. Yeah.
I'm a little confused. In this case, we are considering two particle interaction.
That's right.
What if we have a three particle interaction? Do we take pairwise?
What do you mean by a three particle?
We take three mesons and then.
Oh, sure. You can. No, you don't have to do this. The formalism will take care of it. Suppose you have three ingoing lines and three outgoing lines. I mean, you can even have a system in which there is one ingoing line and three outgoing lines. One meson can decay into three mesons. I mean, assuming conservations, etc. is there. So there is a nice diagram which you can draw with three lines and this, and then you can have loops, etc. So the way I would do this, suppose there are three in and three out, for simplicity, which is what you call the three particle interaction. Then what you would do is that you will consider a term which has 6 factors of j in it. So j1, j2, j3, j4, j6. So that corresponds to 3 particles being produced and 3 particles being annihilated. So you will have a 6-point Green's function sitting there, g of x1, x2, x3, x4, x5, x6, which you have to evaluate. So you have phi 1 to phi 6, then suppose you want to evaluate it to the lowest order, then you have phi 1 to phi 6, then you put a phi 4, and then you do pairwise contraction. Okay?
So anyway, we have to do a pairwise.
Absolutely. Pairwise contraction comes because you are doing perturbation theory, and in perturbation theory, e to the I only the free action sits, and the free action is Gaussian. Therefore, only pairwise correlated. So that is what happens. So actually, you will get a more non-trivial process if you consider a 4 in 4 out formalism, because then you will have 8 factors of phi, and then you will have lowest order, you will have lambda phi 4. To the next order, you will have one lambda phi 4 and another lambda phi 4. So you will have 4, 4, 4 kind of a quantity which you want to evaluate, and then you compute that. Okay.